Okay, so this is a joint project between GA and CSIRO. It's really, we say it's shallow water bathymetry on the AGDC. From GA's perspective, I guess that's kind of our main focus, but CSIRO, as most of you know, work in many different sort of applications of aquatic studies. It's probably going to be one of the first strictly aquatic in terms of coastal type of studies on the AGDC, so there's a few other little challenges we need to address and go through as we develop the project, not least sort of all of the different ones that Norman and Juan Pablo have raised. Primarily we're applying a technique that we've been used in a really regional type of sense into a national scale approach, so how to do that in geographical context in terms of the data volumes and also the different regional ways we parameterise models and whatnot is one of the main challenges. So I'm working with Janet and Hanley here from CSIRO. We also have a guy called Daniel Collins who's from IM&T in CSIRO, and he's working as our Python developer. So I wanted to split it up into three. I didn't want to dwell too much on what we've done in Sambuca in the past, so I'm really focusing on the recoding that we're doing through Daniel, getting it into Python. It's probably good that we didn't really know that there were, or think about having IDL licenses on the cube, otherwise we might have just gone the wimpy route and gone straight down there.
You stay on the dark side. As much as telling these things.
Yeah, we're not too far gone, we still could regress, but
There was no deliberate deception on my part.
You seemed very enthusiastic when we mentioned Python the first time. And we're all in the same boat as Juan Pablo. I think I've done a Python course, I did it months ago and I've forgotten everything that I did there. So we're all going to have to sort of get up to speed with that, but that's just one of the challenges. Then I wanted to sort of go through what we, in this project, what we can foresee that we will require from the AGDC and NCI, and I've sort of kept them as a bunch, AGDC and NCI, because I think that's some of our confusion. Some of the questions which have been raised today and answered in some respects, but some are still a bit vague, is where the AGDC ends and where the NCI begins and where data lives, and all those kind of questions are quite important for our project. And then we're just going to touch on applications and outputs, and again some of the things that Simon raised with APIs and different kinds of things are also things we've identified we need, and how to interpret our outputs and how they get delivered and where they live and those kind of things. So a quick background on Sambuca. It's been around for how many years? Maybe 10 years now?
Our first project was 99.
Yes, okay, so quite a while. So in different versions. It's really a joint method where we're taking a lot of different aspects of field work and theoretical development, and then they all come together in an inversion, which is a physics-based inversion from reflectance data, in which we're trying to estimate from the water column in a coastal environment different aspects of the water column, so concentrations of different kind of things in the water column, what's on the bottom of the ocean floor, so what kind of substrates, seagrass and sand, and bathymetry. And we also have a few different sort of indicators of quality, which are really qualitative in our sense at the moment. As I said, it was written in IDL, and it's very scientific code, not in a good way, in a sense that it was written and it's had bits tacked on and changed, and there's no version control, and it's just, yeah, and plus it's IDL, so put all those things together and it's, yeah. I feel very sorry for giving it to Daniel and telling him that we want it in Python now.
He's been bashing his head against the wall just to get the IDL GUI running.
Well, to the extent where we're thinking about basically just going through the actual principles of the code and saying let's just start from the start and just write it all in Python without even using the IDL code. So we'll see. So it's been used on a number of applications, coral reef applications, but the primary thing is that it's been done on a case study basis. We just pick a case study, generally being very robust about it. We have field work or data or model parameters that are specific to that area, and that's the most robust version, or we can go somewhere else we don't know about and hope for the best. But the underlying theme has been done case study, so we want to see if we can try and move that into a framework where we can do broader scale, national scale approaches, which obviously the Data Cube is set up for. So our aim for the first part of this project, we had a research proposal that was put together and accepted through CSIRO to get it moved into open source, into Python, in view to getting up on the NCI and then being able to use the Data Cube. So I mean, the givens on that are it's going to be a higher processing time, and that's mainly not because of the RAM or CPU speed, because we can parallelise it to such an extent. And gives us the ability to start looking at things such as time series, which we haven't really attacked in the aquatic sphere before. And as I said, it's just a joint project. And that's gone backwards. So we have got 2 stages to this project. The first one, which has been this calendar year, which hasn't got much left in it, is to recode into Python. And the next stage for the next part of the calendar year is to try and get that up and running through different APIs, through different workflow management up on the NCI and working with the data cube. Now, I put interface options here. These are one of the things that's been discussed and probably answered already anyway. One of the things we've been discussing with our sort of development team is what our workflow manager is going to be like, and they were looking at is it workspace, I'm sorry, but it looks like Luigi is going to be the fundamental one that's used on the data cube, so it gives us something to work with. And we're at the early stage of the project where this kind of meeting is great, because then we know which avenues we're pursuing. So we're going to so basically we get the code recoded. Next stage is implementation, having some kind of interface and GUI, because that's important for us. As you'll see, we have a lot of different data inputs that we need to pull together in a smart way to actually get the code to run. Now this is a little, everyone can, I know I haven't done a proper flowchart because all the shapes are wrong. They don't do what they're meant to do, but it makes sense to me. This is basically what our algorithm is trying to do. If we start at the top here, this is our data section, and this is our algorithm section. So over the left here is basically our pre-processing, or I guess in the terms that we've been using here is our sort of querying and extracting from the data cube section. We're reading an image or a spectra. We can parallelize that to the extent that we have enough processors. If it's an image base, we can send a separate spectra or a pixel to each different processor where you have enough CPUs. Then we have a title offset attribution here, which is I've put over here outside of the data, because this is one of the things I've been discussing with a couple of people here. It's a separate code that we need to, for aquatic purposes, attribute a title offset to our time series of data. Because the one thing with coastal environments is that we're not dealing with, when we're looking at things like change detection, we're not dealing with a single constant reading per pixel, because it's always looking at a different environment. We're always looking at a different title offset, or potentially a different title offset. So this will come up a bit later, and it's also something I want to discuss in terms of where that sits, in terms of where that data is stored, how we process that, and you know, the provenance and oversight to that. Then we do a quick correction to subsurface reflectance from the actual reflectance in the data cube, and that's just for our aquatic purposes. On the right, a lot of databases and lookup tables perhaps that we need to have access to, and develop a smart way to working in the interface to read into our algorithm. So we bring in our actual data, and these are really supplementary data. These are the things that we've derived through field work in different regions, other things that we need to make the algorithm work. So that's another question, is where these are actually going to sit in terms of the data cube, where they sit on the NCI, how we get access to them, and also ways that we can use, you know, the location of maybe where we've drawn our spectra or image from as a smart way to grab different variations from our databases. So these all need to be able to interact quite robustly, because different people doing different aquatic algorithms will need to access them in a different way. And this is our interface where we determine all of these things. Won't go into too much in here. Basically what it is a optimization algorithm. So we get in a spectra, we have a forward model, a radiative transfer model, which relates our model parameters, which are the water column and depth, those kind of things, back to our observed spectra. We optimize through that in whatever, at the moment we use a simplex optimization algorithm, until we assess that we have a fit, and there's different ways to do that. You can do just least squares kind of thing, or some spectral match type issues. And then an interesting thing that we thought of with the time series is normally then we'd spit out our output, be it pixel based or image based, and then go on and say that's our result. What we're thinking about hoping to do here in a time series is to spit out our output, be able to adjust that back to a column and datum, for example, using the title offset, then use that perhaps as a starting point for our parameters in our next level of the time series as we move through the time series. So we can, what we're hoping this will do is not only improve our results, and we'll get an ensemble of results across the time series, which you can infer things like uncertainty and whatnot. It'll also help because Landsat's not exactly the greatest data to do this kind of work with. The radiometric resolution is pretty poor, and it's never really been used for aquatic applications extensively. So we're hoping maybe using this time series approach we can maybe get something out of the poorer quality data that we have. And these are some of the stuff that Simon touched on that we didn't really know about. Once we spit out that that result, what do we do with it then? So if we have a parallelized algorithm, we've got to aggregate all of those pixels or our results from our time series into some kind of image or interpretable format. And out of our actual algorithm outputs, we'll then have parameter outputs, so our depth, our different concentrations. We also have a couple of quality control image outputs, as well as the quality control stuff from the data cube, which tell us where we've had run into some kind of error in terms of the inversion, or could be a cloud, could be a land pixel that we haven't masked out. Plus we also have supplementary data that we might want to use if we have existing bathymetry, if we have existing knowledge of the area. And we all want to try and encompass that all in a quality control module, which there might be some version of a workflow API already that exists that we can sort of adapt to, and then use that to then spit out our final sort of output image, where we might want to do a statistical examination of the time series, which Simon showed an example of an API there. All different regions. We haven't really specified what we're going to do with these results yet. We're just sort of throwing it out, and then we get our final image output products. So this is the workflow for our algorithm. What we weren't sure about, or not sure about a lot of things, but is things like our databases. I mean, these have been based on work that Sora is going to be doing this financial year, hopefully, based on a lot of field work and developing these databases for things like water quality components, spectral libraries for different areas in Australia, and also some noise that we associate with the data in an aquatic context. Now, one of the things that makes this a little bit different to our standard applications is A, where they're stored and how we access them, but B, we want to have the option to have them geographically tagged to a regional approach. So if we have a user that's doesn't know what the water quality is in a particular tile, or we're trying to process on a national scale and we don't have fieldwork for all of those, what's the best, given a certain lat long or tile or number, or however we determine that, what's the best one to grab from any of these databases? And we want to have functionality where we can go in and have a user informed, so grab our specific ones, or we have one which is geographically tagged. So it has to be really linked to some kind of lookup based on the location of the tile. So these are sort of very closely linked to the AGDC, so where they live, I'm not sure. And then we'll have a whole bunch of other data sets that could come from previous outputs that we've run. We could run one run on Landsat, and we want to use that as a starting point for a run on, we could run something on Landsat 5 and want to use as a starting point for a run on Landsat 8. So we have those kind of outputs that we want to feed back into the process, and we might have all other kinds of bathymetry data that we want to use as ancillary data to constrain things. So I guess the key thing is they're going to be in a whole different ranges of formats, and again, we don't know where they need to live for effective access and management. So these, I guess, things we want to raise and get people's opinions on as well. Thirdly, this is the tidal prediction stuff that I was talking about. We have code that we're validating against some of the AusTides database from the Hydrographic Office, and it's probably one of the closest things. The difficulty with predicting tides is that we're looking to do it back over a time series of 30 years, and there's just no tidal data available over that sort of, and at the exact epochs that we need for each of our tiles in the database. So we need to have some combination of a model that's using the best data from tidal observations at tidal sites, but we also need a tidal model so we can do predictions into the future, and every time we acquire a new data set or a new tile, we can append a tidal offset to it. And the reason we need this to be pre-computed is because not only do we use it as one of the things in our algorithm, but for all of our other, we're doing some tidal work as well, we need to use it for scene selection, and I think that was, Simon mentioned that. So it'll be one of the filtering type of selections when we're looking through data. We want to say, well, look, we're at a specific tile location, we want to grab all of the time series that are within 10% of the lowest observed tide. So we need to have a lookup table kind of approach to this tidal observation, and be able to use it to not only parameterize our algorithms, but use it as a scene selection tool. Also with coastal masking, most of the applications, all the applications have really been terrestrially based on the data cube so far, so coastal masking hasn't been a big issue, and most of the time we're going to have minimal data in terms of coastal data we want to use, and a lot of it might be terrestrial in a tile. So we wanted to find an effective way to be able to mask an image. Normally we do it just on a threshold basis for our sort of case study locations. And before we discussed with Norman the fact that we've really got to sort of came to the conclusion that we've got a pre-made coastal mask sort of sitting there in the data cube already, where it's sort of water, non-water. There are some things we need to sort of iron out in terms of coastal aspects of water as opposed to terrestrial water. But I think that's the way we're going to go in terms of using one of the WAF's outputs. And it's a good example of how something as an output of another algorithm can feed back into the data cube and be used for another application. So ideally we want to use that. And most of this stuff we've already covered. As I say, we threw these all together before this presentation, and it's actually been quite pertinent. Parallelization is the main thing that we're looking to utilise as terms of one of the strengths of the data cube, because we want to do per pixel applications. Looking at workflow modules and APIs. As I said, you guys are looking at Luigi now, and we've been throwing up what we want to do, and whether or not there are already modules and APIs sitting out there to do stuff like statistical analysis and representation, visualization. I'm sure there's going to be some aspects that we need to modify, but it's good to know there's some modules out there. And yeah, I think that ties in. We've had a lot of our questions answered. We feel a lot better about it and a lot worse at the same time about what we're going through. Applications and outputs. We just split this up into two slides to kind of draw a contrast to what GA is looking at doing, or what our aims are, overarching aims are, and what SIRA wants to do. Not that they're exclusive, but there is a bit of a different focus. So for us, we're really looking at doing national scale shallow water bathymetry. The data cube, what we think is going to give us two ways of doing this. One is the ability to use the highest quality scene. So by using some kind of quality assessment across the archive, we can pick, and we could even do this similar to one published stuff in a best pixel type of application if we have sufficient title data to be able to adjust them back. So it gives us the opportunity to maybe pull out a highest quality scene and then process that just in the standard way with SAMBUCA on a national scale perhaps. Use some of those geographically based inputs to our model and see how that works. We don't have a lot of hope for that, I guess, particularly with Landsat 5 and 7 in terms of the spectral resolution and the radiometric resolution. It doesn't very much lend itself to aquatic conversion, but we can give it a go. But more hopeful is the time series approach, which I mentioned before, being able to pass parameters back into the next inversion to try and sort of start off at a really nice spot in your inversion so it minimises the chance that you get thrown out to a poor minima. And then by having an ensemble of results, so for example if I have 30 years worth of depth estimates across the whole time series, even if I get a few poor results, I'm going to get a distribution hopefully that I can interpret in some meaningful way and say, well, a lot of poor data results makes one reasonable result, and with a certain level of uncertainty. And that also lends itself to doing change detection. And as I said, it's really highly dependent for us. Title attribution is one of the hardest things for us to try and cope with, so it's really dependent on that.